Okay, so this example, let me read it one more time here before I talk about the solution here. So we have a certain volume of a certain concentration of silver nitrate added to another volume of another concentration of potassium iodide. So what is the possible precipitate, and will that precipitate form? So what you want to do, your first step here, okay, your first step is to write the equation out, the chemical equation. So here I've got my silver nitrate, and that's aqueous because nitrates are always soluble. That means it's going to be split into its ions. Potassium iodide is also very soluble from our solubility rules, and also knowing that this is group 1 potassium and this is halogen, those are very soluble. So what might happen here is the silver right here might get together with the iodide, and the potassium might get together with the nitrate. And so those are the ones we need to consider. Now, again, nitrates are always very soluble. So this one is not going to be, this is not going to be the possible precipitate. If you look on your solubility rules, silver iodide is fairly insoluble, okay? It has a KSP number. On the rules, it'll say that this is fairly insoluble. So you'll be able to determine that this is the one that you want to focus on, okay? So the answer to the first question, what possible precipitate may form? Well, that possible precipitate is AgI. That's silver iodide, okay? Now the second part of it is the big part of it, okay? Will that precipitate form? Will it form? So here's how we find out if it will form, okay? What you have to remember is that we need to find out if there are enough ions in solution, okay, to actually multiply the product of those ions of silver and iodide. If that product is high enough, large enough, then it will form a precipitate. Those ions, if there's enough of them in solution, they will actually get together and they'll form a compound, right? So how do we know that? Well, we know this little thing about the trial KSP. Now the trial KSP is this number, the KSP at room temperature. So this is the KSP that's published, okay? So this is the published KSP from the chart. KSP of silver iodide would be 8.3 times 10 to the negative 17. It's pretty low. That means you don't need a whole lot of ions in solution to multiply to a number greater than this. That is an extremely small number. So let's go over here now and let's find out, let's find out how we figure this out. So I take silver nitrate. That's going to break up into silver ions, a 1-to-1 ratio of silver ions. So I take my volume right here, 10 milliliters is 0.010 liters, and I multiply by my concentration right here. And I get this number right here, 0.0010 moles, which means 0.0010 moles of silver iodide ion. This is very important right here, okay? Now that's moles in solution, okay? That's moles, so I need a concentration for KSP, all right? But let's take a look at the iodide. So where does the iodide come from? Well, it comes from here, and I've got this many moles per liter. So I'm going to take 90 milliliters, that's 0.090 liters, times my concentration, which gives me this number. That's the number of moles of iodine that I have, okay? So I've got moles of silver ions, and I've got moles of iodide ions. I'm getting close now. What I have to do finally though, because the KSP always works in concentrations, so this isn't good enough. I need to figure out what the concentration is, not just the number of moles, because it depends. If I have a certain number of moles and it's in, it's in a container as big as this classroom, then that's not a lot of ions, right? But if I have this number of moles right here in a small beaker, that's very concentrated, so the ions there's lots of ions in there, really. So I need to find out the concentration. So you must use molarity. That's this little note right here. That's the moles per liter. So I take the moles of silver and I divide by and this is important because I've got 90 mils of one and 10 mils of the other. So think about that. I've got 90 mils, right? And I'm adding it to 10 mils of the other one. So that equals 100 milliliters, doesn't it? which is 0.10 liters. That's why I'm using this number right here for my volume. That's the volume of the new solution. So I take my number of moles right here, divide it by the volume of the new solution, and I get my concentration, capital M, of Ag+. I do the same thing with the I. I take the moles from right here, I don't know if you can see that, the moles from right here, and I divide it by my volume, and I get this concentration. Okay, so at this point right here, this is super important. I've got these two numbers. Now what I do is I look at my compound, and it's a 1-to-1 ratio, so that's a real easy calculation for the trial KSP over here. I simply, my concentration for silver to the power of 1, and times my concentration for iodine to the power of 1. This right here is my trial KSP. So this is what the KSP multiplies to in my example, or in my trial. And that's where you compare the two KSPs, the trial. So here the trial KSP, it's larger than the published KSP of 8.3 times 10 to the negative 17. If that is the case, literally, we have more ions than we need in order for them to accidentally bump into each other and to form a compound and to form a precipitate. So because this KSP for the trial KSP is much higher than it needs to be, then a precipitate is formed. Okay? So that's just the run over of how to do an example like this, predicting precipitation. You want to use your solubility rules to find out what compound might actually form. Then you find the concentrations of each ion and multiply it according to the KSP, and then you'll be good. Remember, if this was a compound like let's say it was Ag2I3, let's say, okay, well, no problem. Then you would change the exponents down here. This would be a 2 and this would be a 3 then. No big deal. Okay, if that was the case. Okay. Okay, so let's take a look at this question. This is an ICE chart question. Finding equilibrium concentration. So remember when we did this unit, we were given some kind of sealed container. Okay, so let's just say it's a square sealed container here. And in this question, it tells us that this is a 2-liter container, 2 liters. And inside this container, we have somehow injected into this container 0.4 moles of nitrogen. So we've got N2, and that's 0.400 moles. And we've also injected O2 gas of 0.400 moles as well. Okay, so that's in a sealed container. And that's this part of the reaction that you see above, okay? So we've got initially we've got some of this, but we have none of this at the beginning, okay? Before this is reacted at all. So this is sort of the setup, okay? And then what happens, it says they have reacted to equilibrium. So that means that the nitrogen and the oxygen have reacted, they've reacted and they've gone in the forward direction as far as they can go to produce NO, and then at equilibrium, that's when we have this delicate balance of forward reaction and reverse reaction, okay? So at equilibrium, we have some of everything. We have some nitrogen, unreacted nitrogen, some unreacted oxygen, some nitrous oxide, okay? So we have a little bit of everything. And the nitrogen that maybe exists at equilibrium is not necessarily unreacted, that hasn't reacted at all. It's maybe reacted and then come back to its elemental form. So we initially just have this, and then at equilibrium, as this moves towards equilibrium, now we have a little bit of everything. So we have some N2, which we don't know how much we have. We have some, O2, which we don't know exactly how much we have. And we have some NO, which again, we don't know exactly how much we have. So this is what we're trying to find here in this question. What are the equilibrium concentrations of all of the gases? Okay, so the setup of the question, you understand the setup of the question?
I think so.
Okay. All right, so how we do this is we use ICE charts. So this is where ICE charts come in. And ICE, this stands for initial. This stands
Yeah.
for change, and this stands for equilibrium. Okay, so that's what the 3 rows stand for. ICE.
Okay.
Okay.
Like
Now,
the first row, the first two, you put like the initial amount we have, so 0.400 molar.
well,
And it goes for the other one.
well, okay. Now pause for a second. You got to be careful there. We do put the initial amounts in the top row. However, and again, I would remember how I always kind of tell you to put the sort of the substances in the reaction above each column. So we'll do that first. Make sure you do that along with the coefficients too, because that's going to be important. But what you said there, putting the initial amounts is correct, but not 0.4 moles. Not moles.
0.4.
Not moles. It has to be concentration. It has to be concentration. So notice that we have 0.4 moles in 2 liters. In 2 liters. So that's 0.400 divided by 2. That's 0.200 molar. And that's what goes in here, 0.200. So it has to be concentration, initial concentration, change in concentration, equilibrium concentrations, okay? Very important.
Okay.
So we've got 0.200 for each of these first two. And then what do we have?
0 for the last one.
What do we have initially? Yeah, we have 0 for this last one, correct. Because this is at the point before anything has happened, really, just before anything has happened. Now, in this movement here to equilibrium, this is the change part, okay? So what's happening? Well, obviously this nitrogen is reacting with this oxygen. So this is going to go down in concentration. That's why the negatives are there. NO obviously is 0, and it's going to go up in concentration. So the signs are going to be negative, negative, positive. That's the first step. The second step is to try to represent somehow what this change might look like. Now, we don't know what the numbers are at the end, so we don't actually know right now what the numbers are in the change. So that's where we represent this now by a variable. It's an unknown amount. But what's important here is that we use the coefficients 1, 1, 2. So 1, 1, 2. These are very important in this middle row. So I go down by some unknown amount. I can just represent that as a x, and more specifically as a 1x, because it's going to go down 1 times this unknown amount. This one is also going to go down 1 times this unknown amount. All right? And because of this 2 here, for every 1 mole in change, I'm going to add 2 moles of the same change. So, okay? So that's why we have to use the coefficients.
Okay.
You don't have to write the ones, obviously. I just wrote that for explanation.
Yeah, I understand.
Okay. All right. So that's very important. That's very important. We don't know what the change is, but we can represent it by variables here. And these have to be in relation to one another. 1 to 1 to 2. Negative, negative to positive. Okay. So finally, equilibrium, we go ahead and we go 0.200 minus x. Why? Because this is what I initially had, this is what it changed by, and now that I'm at equilibrium, I have the sum of these two. So this is like this as well. And then this is just 0 plus 2x or 2x. So the ICE chart is very helpful because it helps us to systematically get the representations for the equilibrium concentrations. So now I have representations of what these should look like. How much, like how big this x is right here, how big that x is depends upon the actual KEQ. So the KEQ is a measure of, how much this changes, right? So if we have a KEQ that's less than 1, that means that the forward reaction is not as strong as the reverse reaction, or we have more reactants when we're all said and done. We'll have some products, but we'll have a little bit more reactants. If this was a very large number, that means that we would have way more products. So we have to use this number now, so let's do that. So the KEQ is 8.00 times 10 to the negative 2. And maybe I should back up. The KEQ equation is this. It is the concentration of NO as a product on top squared because of the coefficient divided by the product of the reactant concentrations, so N2 times O2, each to the power of 1 because 1 is their coefficient. So that's the KEQ expression. You remember that?
Yeah, I do remember that.
Good. Okay, so now let's start filling in values or expressions at least. So I have my KEQ over here on the left. Now I'm going to put 2x on top, and I'm going to square that because that's what my NO is at equilibrium. Because remember, this is at equilibrium. So underneath here then I have 0.200 minus x times itself, or that is 0.200 minus x all squared, because I multiply it by itself here. You see that?
Yeah, I can see that.
All right, what you want to see, what you want to notice here is this, okay? We're going to try and solve for x, and this is where the math kicks in, okay? This is why in Chem 30 you have to have a little bit of math background for times like this. But what we see is that we have the top is squared and the bottom is squared. Now that's really good because that actually, if you know your math, that actually can be rewritten. Whoops, I erased, oh shoot, I erased too much there. This actually can be written like this. It can be written as this whole thing squared, top squared, bottom squared. It can be written like that, which means that, hey, in order to get rid of this squared, we do the opposite operation, or we take the square root, and what we do to one side, we have to do to the other side. Okay, you remembering this?
Yeah, I'm remembering this.
Okay. I'll get my calculator up on the screen here so I can show you what I'm doing here. There we go. Okay, so let's turn this on. And what you want to do then is you want to put in, come on now, clear. So 8.00 times 10 to the negative 2. So 8.00, and the scientific notation button is this EE button on my calculator. So try and find your scientific notation button on your calculator.
I just have times 10.
Well, you're gonna have to be careful if you do multiply 10 to the power of. Just have to be very careful if that's gonna work. You should have, if you have a scientific calculator, you always will have a scientific notation button on a scientific calculator. So you should probably get into the habit of using that, because I've seen students do times 10 and then to the power of something, and their calculator does not do that properly. So just be aware of that. It could look something like this, right? It could look something like that. It could be EXP as well. That's another button. Or it could be
mine looks like the first one.
Times 10 to the x?
Yeah.
Yep, use that button then. Yep, use that button. Okay, so what I need to do, I didn't put the square root in first, but so let's do that now. So square root of my answer here. So you need to put the square root of this. That's what we're doing.
I did.
That should be 0.2828. Did you get that? Did you get that?
Yeah.
Yes? Okay, so that means that over here I have just simply 2x over 0.200 minus x. So I've gotten rid of the squared. And now this is going to be pretty straightforward, because what you need to do is multiply both sides by this 0.200 minus x to get rid of this on the bottom. And that over here gives us, so 0.2828 times 0.2. Come on now. 0.05656 minus 0.2828x, when I multiply this times this, equals 2x. And continuing on, let's add 0.2828.
How did you get that previous one?
2828x. How did I get the previous what?
How do you get
this line right here?
Yeah.
So I multiplied this 0.200 minus x times this right here.
I'm confused.
So 0.2828 times 0.2.
0.2. How do you get that?
All right. So we will get rid of the x's on the left side, and so I have 0.05656 equals, this is 2.2828x. Now I'll divide, to get x by itself, divide by 2.2828. both sides. 2.2828 to get my x value here. So we'll take that number and we will divide. Oops. Oh, now it's not going to give me that. Oh my. Okay. Point. Was it 0.56? 0.5656?
Yeah.
Divided by 2.2828. 0.02477 I get. 0.02477. So that's what I get for an x value. Okay. So that should be what you get for the x value. Now, here's the thing. Oh, actually, I should say a couple things. When you take the square root of this number, technically it's positive or negative, but we're not going to be worried about the negative values here because just use the positive values, right?
Yeah.
Now, the other thing is this is x value. This is not your answer. You have to now use this x value, okay, to calculate this value right here.
Yeah,
And
then that's
this
your
value.
answer?
And this value. So the concentration of N2 at equilibrium is going to be 0.200 minus 0.02477. That's what your actual concentration is going to be. So we found out that that little change is actually 0.02477.
Okay.
All
And I
right.
just plug each of the
0.17522.
I'm looking for. So it's in this case the equilibrium. Once I find those answers, or that's the final answer.
So O2 is going to be the same. And then you just multiply this 0.02477 times 2, 0.02 times 2, and that's going to be 0.04954. Oops. 04954, I think that was. Okay, and that's going to be for NO, the concentration of NO. The only other thing you'd want to do here is take a look at your significant figures at the very end. So we have 3 sig figs, 3 sig figs, 3 sig figs over here as well. So we have 3 sig figs in the KQ. So 3 sig figs is what you're going to want to round this to. So this is going to be 0.175 molar. And this is going to be 3 sig figs, 0.0495. That's a 4, so that can just stay. And this will be molar as well. Okay?
Okay.
So those, I think those should be your answers there. Let's just double check. I think I had the answers jotted down here somewhere. Oh, maybe not. I'll go back and check.
Yeah,
All right, so that is your final answer for your ice chart question there as well. So hopefully that predicting precipitation and ice chart review helped you. Any final questions?
So